So this is the problem called lifting boom 1. That was the heading, I guess. So I've here made the diagram. You can see here. This is your this would be your rod. This is your mass hanging from the rod, and this is the point where the rod is fixed to a support by using this rope, and this is the tension in the rope. These are some variables we are going to use. Capital M for the mass of the crate, small m for the mass of the boom, L for the length of the boom or the rod. Then these are their values. I have drawn a diagram again here in a elaborate fashion. You have theta, the angle. Notice that theta is with the y-axis. Then you have tension, then you have the two weights and some distances that I have marked and I have calculated here. Look at D2. If this whole length is L, then D2 is just L sine of theta. Remember, theta was with the y-axis, so this will be L sine of theta. Similarly, D4 would be L. Now it's D4 would be L cos of theta, and then I have calculated those values here. Right. Now, since the problem is in equilibrium, meaning there is no net torque or no net force acting on the system, and we can use this equation that sum of all torques on the system is 0 to our advantage. Now all we have to do is list all the torques that are acting about on the system, and to do that we need to find a pivot point around which we are going to calculate our torques. You can choose any of those points, but we have to be a little more careful about it. We can choose B, we can choose O, it would work fine. The wise choice to choose O is because first there's a force here, the force between the rod and the support, which we have no idea about. So by choosing point O here, we are technically ignoring that force, and that helps us with our calculations a lot. So now about point O, what are the forces? Well, I'll write that force F as well, F into 0. Now we know about moment arms and the forces and how their combination gives us the moment. So we'll just list those forces. First, let's list tension T, and the perpendicular distance would be D3. T D3 similarly with the weight of the crate and the weight of the rod. And then finally for the force F. If F is force acting on point here, acting on O, then the perpendicular distance from this line to the point O, or from any line passing through O to point O, is always going to be 0. So that force is not going to come in. Whereas if we had chosen some other point, that force would have come into picture, and we having no idea about that force wouldn't have been able to complete our computations. So now this equation is pretty straightforward. You have T D3. Let's leave it at this side and take everything on the other side. Taking out G common, you're left with this equation, and putting in the values you get this. So that's the value of the torque for this problem. I guess that's that. Solved. Let's look at another problem. We'll do it this one in a bit detail. This is the problem where we again are given a system and we have to find the tension in the system. We have to find this T. Again, I've drawn the diagram and expanded upon it here. Let's first understand the system. We have a rod, we have a mass hanging from the rod, and then we have a rope or a string providing the support, and we have to find the tension in that string. Now let's look at a better diagram here, or one with more details, so not technically better. You have tension T, then we have divided the tension into its components, makes our calculations easier. The weights, this is the mass, and this is the weight of the rod. I've put in the values here, and similarly, like last time, I've calculated the distances. Now these distances are a bit tricky, but if you look at the diagram given in the question, you can easily see that these are the values they amount to. And then we have calculated theta as well, and theta we have gotten using this triangle. You can see that this is d2, uh, d2, and this is d4, and the combination will give me tan inverse d2 over d4, from which I can calculate my theta. So now we have all the values we need. Again, we are going to use the equation of the torque, because the system is again in equilibrium. But here, let's first find out what happens if we find the torque about any other point. Let's see why we cannot choose B as our point. Recall that torque is nothing but R cross F, and which you can write it as, if you want to find the magnitude, as dF, where d is the perpendicular distance from the line of action of the force to the point where you're trying to find the torque. Okay. Now, about point B, why cannot I find the torque about point B? Or why is, well, I can, but it's not going to be much useful for our problem. But why? Let's say that you want to find the torque about point B. What are the forces about point B? I'll just do a bit here so that this doesn't impede our main calculations. What's the force on point B? Or the forces about point B? First, let's do t cos theta. I think the point will be well established by just this one. T cos theta. Now, see, t cos theta is this point. What's the perpendicular distance from this line to the point B? 0. Similarly, for t sine theta, you get 0, plus so on and so on. Now, these two are the terms which have all the information about the tension. And since we want to find the tension, these zeros will nullify that information, and we are left with nothing. So we cannot find tension by choosing our pivot point as B. We have to move somewhere else. Like last time, let's just choose oh, now let's and our axis. We have to choose our axis too. This is our positive axis. Always do this exercise first. Choose your axis. Okay, this is our positive axis. Now let's find the torques. What's the first torque that we should write here? It's negative t cos theta. What's the distance? Perpendicular distance to, that's t3, plus t sine theta. Now what's the perpendicular distance? That's d2, right? d2, okay, plus this would be minus capital mg. What's the distance from capital mg? That's d1, the perpendicular distance, right? Mg is downwards, the perpendicular distance from, that's d1, and then minus mg d2, and all of them amount to 0 by virtue of this equation. Okay, so far so good. Now we have to solve this equation. Let's take t common, and you are left with d2 sine theta minus d3 cos theta is equals to, let's take g common, md1 minus md2, and tension is simply g md1 minus md2 over d2 sine of theta minus d3 cos of theta. And if you plug the values in, which I hopefully have done correctly, please recheck, you get these values. Now this is your tension. Okay.